Hello, welcome to the first class of my Algorithms Huddles series. The topic for today is depth first search, but it's depth first search deconstructed. So I'm assuming that you're already familiar with depth first search. We're going to look at what we already know about depth first search and just dig around that a little bit, okay? So sliding right in to DFS 101. What is the basic idea? We have a search space of distinct entities or nodes, and they have pairwise links called edges. What is the contract of depth first search? The contract is, well, depth first search, first of all, is defined on a given start node. So what would DFS in this particular example, what would DFS on A? What does that mean? The contract of DFS of A would be to visit all the nodes that are reachable from A in depth first search manner. What does that mean? What is depth first search rule or depth first search way? It's quite simply to pick one neighbor and go deep into that neighbor. What does that mean? In this particular example, we are looking at DFS of A. It has two neighbors, B and C. We first explore all the nodes that are reachable from B. And once we are done exploring B depth first, so going as deep into B as we can, then we come back to A, and then we try its next neighbor. In this case, that is C. And then we go explore all the nodes that are reachable from C, and then we are done with depth first search of A. So that is the basic idea. Now, I mean, it's simple, but not that simple. So let's nitpick a little bit on the contract that says DFS of A is to visit all nodes reachable from A. A few caveats is, first one, what if there are cycles in the graph? And even without cycles, what if there is a particular node, in this case, let's say D, that's been highlighted? What if the node D is reachable from both B and C? So if we are doing depth first search on A, it has two neighbors, like in both of the examples on top, it has two neighbors, B and C. Should depth first search of B and depth first search of C, should they both cover node D? No. And this is where the concept of keeping track of a set of nodes that has already been visited across the various DFS calls so far, that's where it comes from. And this is where we have the data structure visited, which is a set of nodes that have already been explored by depth first search. So this changes the contract a little bit. Visit all nodes that are unvisited and reachable from A. A tiny bit more of nitpicking here. Look at the case down below, that where you have this node A. So let's say you did depth first search on A, and that calls depth first search on B. And at this moment, when depth first search on B has been called, if you look at node C, it is both unvisited and reachable from B. There is a path from B to C. But depth first search of B is not going to explore C. So I guess our contract is not entirely correct, is it? Because we are saying visit all nodes unvisited and reachable, but that's not what we are doing. So how can we change that? We can come up with a new definition. So why would, just to step back a bit, why would B not visit C? Because the only way B can visit C here is via A, which is already visited. So let's make a quick definition called unvisited reachable. So C is not unvisited reachable from B. For C to be unvisited reachable from B, B has to be able to go to C using a path that has only unvisited nodes on it. And so that makes C not unvisited reachable from B. So that's brings a little further clarity to our contract. Is DFS of X. Now the function header changes, has the data structure visited in it, and the contract is to visit all nodes that are unvisited reachable. Well, I just want to fix this really quick. Sorry about that, because it's not, we're talking about X now. So, okay, visit all nodes that are unvisited reachable from X and assume that X is unvisited. Okay, so looking at the basic structure of the code, and I'm sure this is what, this is what our classical knowledge of DFS includes, is this code. And so I just want to put it back up there. DFS of X comma visited. Usually the first thing we do is mark X visited because we're on it now. And then we just have this for loop that goes over all the neighbors of X and then do DFS on each neighbor. But before you do DFS on each neighbor, check if it has already been covered by one of the previous DFS calls. And there are some other variants of this code where you would do the marking of a node as visited before you call DFS on it. So you have a few choices in terms of where do I mark a node visited and where do I check if a node is already visited. So if you see some DFS code out there, you might come across another variant of this code. Just wanted to point that out here. And time and space complexity, just a quick reminder, the time complexity of DFS is order V plus E, where V is the number of nodes and E is the number of edges. A very quick way of understanding this is DFS is not called, at least using this variant of ours here, DFS is not called more than once on a given node, so we have no more maximum order V calls to DFS, and we have maximum order E checks, that if loop, if Y is not visited. We won't check it more than once for every edge. So in the worst case, the work we will do is order V plus E. The space complexity is order V because I guess in the worst case, the entire graph could be one big cycle, and then we will have all the DFS calls active at the same time on the stack. Okay, so that's the time and space complexity in the basic DFS contract and code that we see out there. Next, we look at, just wanted to point out this phenomena of when the input graph to DFS is not fully connected, then what's going to happen? You will call DFS on one of the nodes. It's not going to end up covering the entire graph. So just pointing out that DFS to a randomly chosen node of a graph is not guaranteed to cover all the nodes of the graph. So if you want to do DFS on a graph that is not fully connected, you might need multiple starting DFS calls. So to illustrate that with an example, on the top here we have a graph. So this whole thing is a graph, this here. So that's your input graph. And as you can see, it has two components. One is A, B, and C that are all connected, and then D and E are part of a separate component. So here we will need multiple starting DFS calls, right? So the way we usually do it, and you will see this in code everywhere where you look at DFS on a graph, is just have an outer wrapper. And what this outer wrapper does is, well, it initializes visited to empty, and then for all the nodes in the graph, just iterates in a for loop over all the nodes in the graph. And if the node is not visited, it just calls DFS on it. What's going to happen when we run this outer wrapper on this particular example? Let's say the sequence in which it processes the nodes is A, B, C, D, E. Then what's going to happen? It's going to call DFS on A because A will not be visited in the beginning. And that DFS on A will end up exploring A, B, and C. Then it's going to try and call DFS on B in this, let me highlight this, in this for loop here. It will not call DFS on B because it's already been visited, and it will not call DFS on C because it's already been visited. Then it will try and call DFS on D, which will actually get called, and it will end up covering both D and E. And then it will try E, and it will not call DFS on E because it's already been explored. So that's just the story of the DFS outer wrapper. And I've added another quick example here on the side to illustrate that it doesn't have to be a graph that doesn't look fully connected. This one kind of looks connected, but as you can tell, if you call DFS on A, it will cover A and B, but it won't cover C. So that's kind of the point behind the outer wrapper. All right, moving on. 3 more things I wanted to point out about DFS, and hopefully you'll enjoy this, or it'll be a good reminder of what you already know. Timestamping, backtracking, and the idea of a DFS tree. So let's try timestamping. Okay, we're gonna actually run DFS on this graph that we have here, and we will timestamp every node with the start time when the DFS started on that node and when DFS was done, when the call to DFS is finished on that particular node. By timestamping, we're just using a simple global counter. Okay, so let's do this. So we are starting with DFS of A. So the counter right now is 1. DFS has started. Let's say it visits its neighbor C first. Now the timestamp, the timer is 2. The global counter, excuse me. So C's DFS is starting at time 2. Then let's say C goes to its neighbor F first. 3. F does not have anywhere to go. It only has one neighbor C, and it's already been visited. So we're done with F, so that's 4. That is the finish time for F. Then F goes back. We'll do these in dotted arrows to C. C is still not done. C actually has 3 neighbors, A, F, and G. A is already visited. F has already just been visited by C, so now it's going to try G. So now it's going to go to G, and the time now is 5. G is going to, yes, only one neighbor, B, and time is 6. And B is now done because it has 2 neighbors, G and A, and they're both already visited. So B is done at 7. It comes back to its caller, G. G is now done at time 8. It goes back to its caller, C, who is now done at time 9, and goes back to its caller, A, who is now done at time 10. So now we have, this is the time stamping, right? All these times. And this can be incredibly useful in certain applications of DFS. There can be some interesting information that we can extract about the nodes based on their start and finish times. So it's one good thing to know about DFS, that you can enhance it with this time stamping. Backtracking, as you already saw in our working of this particular example, is inherent to how DFS unfolds on a graph. It's not just a side effect of using recursive code to implement DFS. I would say backtracking is so inherent to how DFS unfolds, and that recursion is just a beautiful fit for it. So backtracking and recursion are just an excellent fit for the nature of DFS. Okay. What was the third thing? Yes, DFS tree. So every DFS walk on a graph imposes a DFS tree that captures this particular trace. So if you look at what we did here, we started with A. A actually has 2 neighbors, C and B, but it did not end up exploring B. So A only went to C, and you can see this is the graph that is here. A went, the tree, A to C, C went to F, and G went to B. So DFS walk on every graph imposes a DFS tree that captures this trace. It's just good to know, might or might not be useful, but it does deepen our familiarity with DFS. Okay, moving on, observations so far. We did a bit of nitpicking on the contract of DFS and really clarified it. That felt good. Unvisited, reachable. We learned about timestamping, DFS Tree. We noticed that not all edges are walked. If you go back to this example, you can see that the edge from A to B was never really walked by DFS, just something to note. And that backtracking is, and going back to the caller node, is quite inherent to how DFS unfolds. Okay, so pause. Now we're ready to dig a little bit more. Let's look at DFS unfolding on a tree, on a directed acyclic graph, maybe a directed cyclic graph, and see if there's anything to note. And then we'll do a little compare and contrast with DFS and BFS. Okay, DFS on a tree. As you can see, I have the example here, and now you guys know what all this drama of edges and dotted edges means. DFS being called and then returning, and then you know the start and end time. So I've just added it here in case you want to pause and really kind of revise how DFS would work on a tree. Now, tree gets handed to us usually with the root node, and the call to DFS there will end up exploring the entire tree, right? So what can we note here? Well, first of all, there are no cycles, and there is no need for visited, because for every node there is only one incoming edge from its parent, this being a tree. So that's the first observation. Second one is that the DFS tree is going to be same as the input tree, yes, and each edge will be walked. Okay, it's good to know. Moving on to DFS on a directed acyclic graph. These are my favorite graphs to do DFS fun with. We definitely need visited here. We already saw that in an earlier example. As you can see here, that there are no cycles. This is a directed acyclic graph, but we still need visited because we don't want to do the extra work, right? By the time for example, A does not want to explore E because A does explore E. What is a good example here? Okay, when we come to DFS of E, we are not going to have, we don't want to go back again to B, right? Does that make sense? Yes, that one is good. Because B, the DFS on B has already done and happened. So it's just something to note that in directed acyclic graph, it's not about infinite loops as much as it is about avoiding extra work. And if you want to understand this further, you can pause the video right now. You have how DFS exactly unfolds on this directed acyclic graph, and take the time to really understand this, that it's not about infinite loops if there are no cycles, it's about extra work, okay? Timestamping. We already know what timestamping is, but in directed acyclic graphs, there is timestamping takes on a little bit more meaning. So if there is an edge going from node X to node Y, Y is going to finish. DFS on Y is going to finish before DFS on X. Doesn't matter what node you started your DFS with, doesn't matter what the outer wrapper did and what exact sequence did it go over all the nodes. Y will finish before X, and this observation is key to the linear time algorithms to do topological sorting of all the nodes on a directed acyclic graph. So this is a really powerful, and this is where timestamping becomes really powerful. And nothing too tricky, but the DFS tree is obviously not unique. It's going to be completely different based on where you start your DFS. Here we started it on A, and this is the DFS tree we got in purple below, but you can try starting DFS on some other nodes here, and you'll see that you'll get a different tree. Okay, DFS on a directed cyclic graph, so it's directed, but it does have cycles. Okay, not a whole lot different than an undirected cyclic graph, but I just wanted to include it here. Visited is obviously needed because we can have infinite loops. And if there is an edge going from node C to node A, there's nothing we can guarantee about the finish times. A can finish before C or it can finish after C, as you can see in the two examples on the left here. So that's kind of interesting that cycles remove that particular observation that we had on timestamping. Does not have that nuance to it. Okay, how about DFS on undirected graphs? Well, we've already seen that, so I must have included this here just for completion. Visited is a must-have because we can have infinite loops. Timestamping can be informative, but maybe not as useful. It doesn't have the same nuance, like we just said, as in acyclic directed graphs. How can it be informative? If you just look at the timestamps here, for example, let's just pick on one node. Let's look at C. So C has start time of 2, finish time of 9. And if you look at the DFS tree here, let me highlight the C part. So this is the DFS tree rooted at C. And this subtree has 4 nodes in it. And the start time of C as DFS unfolded was 2 and the end time was 9. And this will be true for every node, that you can determine the size of the subtree rooted at a given node in the DFS tree by looking at the start and finish time. So it's finish time minus start time divided by 2 and taking the ceiling of that. So I'll leave the details for you to work out, but I just wanted to point this out that don't give up on timestamping just because there are no, if there are cycles still, it could have some information in it, and who knows, it could be interesting. It could be interesting for some problem out there. Okay. All right, so that was, we looked at DFS on trees, directed acyclic graphs, directed cyclic graphs, undirected graphs. Okay, now this can be an entire class on its own, so I'm not going to cover it in its full depth, but I thought DFS Deconstructed would be just sort of incomplete without at least a little compare and contrast with BFS. So we have this 2 examples. I think it's just good to see some of these differences by using a simple tree. So I have the same tree, and we are going to do BFS on one, and then we are going to do depth first search on the same tree, and then make a few observations. So let's dive in. So let's do BFS this side on the left tree, starting at the root. This is how trees get handed to us. So now we go to B, starting at time 1, and then actually let's not do time stamping. We'll just notice the sequence in which the nodes are visited. What is the sequence in which we are covering all the nodes and all the, let's just look at it from that lens. So I'm just going to timestamp every node with when it got visited. So 1 for A. Now we're going to visit B, then we are going to visit C, right? That's breadth first search. So now we're done with level 1. Now we are going to visit D, E, F, and G. So that's going to be 4, 5, 6, and 7. And I think there's no need to worry so much about edge walks right now for breadth first search. So I just want you guys to look at this. So breadth first search of A is going to visit the nodes in the following sequence: A, B, C, D, E, F, G. And we already know that, and I've put that sequence at the bottom here. Let me circle that. So look here. So this is BFS of A, B, C, D, E, F, G. If you look at BFS of the node B, if we were to do breadth first search just on node B, then that breadth first search will go B and then D and E, as it's highlighted here. Okay? And I just wanted to point this out. So this is breadth first search of B, this is breadth first search of C, and this is breadth first search of A, correct? And as you can see, B, D, and E, which is the sequence in which breadth first search of B will visit the 3 nodes underneath B, it's not all together in breadth first search of A. And the reason I'm pointing it out is that breadth first search of A doesn't include inside of it breadth first search of B. Breadth first search of B is kind of scattered a little bit. So it's not inherently a recursive algorithm, breadth first search. Extremely powerful for some particular applications, especially those involving shortest paths. And hopefully we'll get to cover some of those in a future class. So I just wanted to point this out about breadth first search, that it is not inherently recursive in nature, and the data structure of a queue naturally facilitates the bookkeeping of what the current state is and what the next action for breadth first search will be. Now moving on to depth first search, you guys already know this now, and you have been reminded very well with all the mess we made earlier with depth first search. Depth first search on this tree is gonna, unfold starting with A, then going to B, then going to D, all done with D, come back, then going to E, all done with E, back to A, and then from A it's going to C, which is the 5th node visited, and then 6 and 7, right? So, and here, as you already know, a stack naturally facilitates the bookkeeping that's required of current state and next action. And if you look at depth first search of A, the entire sequence, it is, let me circle this so I know which part of the notes of the whiteboard I'm talking about, this part. So depth first search of A is A, B, D, E, C, F, G. Depth first search of B is B, D, E, which is included as a substring in the depth first search of A sequence. And I just wanted to demonstrate that about depth first search, that it is an inherently recursive algorithm. Now, the other thing I wanted to point out that's up here is this. Depth first search produces a traceable walk. So if you were tracing the graph as depth first search is unfolding on it, you wouldn't need to lift your hand. So just to demonstrate that very quickly, let's choose a color, okay, to do the highlighting. So you are on A, from A you went to B, from B you went to D, and so you can just come back from D, then you're going to E. So whatever you want to do next is always a neighboring node, whether it's going to a neighbor or whether it's going back to your caller. And from B you go back to A. So as you can see, this is a trace. Yes, so it's all one trace. You can do it without lifting your finger. Not the case with breadth first search. So from A we chase this edge to include B and then C. And now after C we gotta go to this edge, right? So this traveling from C to B. And so it's not a super technical issue. It's not like, oh, we have to know this, but I think it's a curious thing to know about depth first search, which makes depth first search a really good fit for certain applications where maybe we might not naturally think about it. For example, if the search space of distinct entities, your graph, your input graph, if it is laid out in the form of a physical space, let's say a grid, and you want to cover the space using a robot, then I'm setting this up a little bit, so I feel like I'm cheating a little bit because I'm going to do my next video on the robot room cleaner problem, which uses depth first search. But the reason depth first search is such a good fit for those problems is because of this attribute of it, that it produces a traceable walk. It's not exactly the depth first nature of depth first search that's sometimes needed to solve a problem efficiently. It's this aspect of it. So I just thought I'd point it out. Okay. So final observations, we learned a whole bunch of things about depth first search. I think we made a decent sized mess. We looked at unvisited reachable, timestamping, DFS trees. Hopefully, if you want to revisit it, you can go back to that particular slide in the video, pause it, and look at it a little bit more, work it out for yourself. As always, feel free to send me any questions if you want a clarification, or if you find a bug, I'd be happy to add some comments as part of my video or add some subtitles to point out my mistakes. So these are just a summary of everything that we did today, okay? That's it. Is that everything about DFS? And a particular question that was actually asked of me by more than one engineer when I was teaching them something similar was that they felt a little bit bad that they didn't already know this stuff. So if I'm a worthy, esteemed CS student, software engineer, etc., shouldn't I know this already? Well, I think for those of you who know me, know very well that my answer to both those questions is no. It's a resounding no, you guys. No, this is not everything about DFS. I'm pretty sure there's plenty more, and that a bigger mess can be made. And absolutely no, a huge loud no to that second question. If I'm a worthy, esteemed CS student, shouldn't I know this already? Of course not. Usually depth first search comes to us. We learn depth first search and many concepts in computer science. We learn them on our way somewhere else, on our way towards completing your course, on our way towards lead coding if you're preparing for interviews, on our way to learning maybe something about graph algorithms. So usually, the input comes to us as a graph, adjacency lists, and we learn classical DFS with the code and the contract on it, and it's not the most conducive way to learn all these nuances. It doesn't make it the wrong way. I think it's fine. Learning is, this series is about learning algorithms, and it is especially targeted to engineers, because I think engineers, we like to live in that middle space where we don't have the time or sometimes even the inclination to go full on academic rigor on everything, but practicality of our job where we are making so many decisions based on partial knowledge, we get particularly good at looking under the hood beyond the help page of a data structure on an algorithm and just getting to the story of it and making decisions based on that. So this is what this series is going to be about, not full on academic rigor and not just looking at the usage or the API or the contract of things. So learning more about the story. And that learning can be hard on knowledge. And this is one of my favorite quotes of all time. Learning is hard on knowledge like kids are hard on furniture. So if you are feeling a sense of discomfort when you learn something a little bit deeper, I just want to point out that the discomfort belongs and it doesn't mean anything. Learning does include some unknowing. So hopefully you guys had fun, and I will see you in the next class. Bye.